Folks. This is a follow-on video from the one I recorded a few weeks ago about how I built a database containing the names, the chemical structures, and eventually the properties of many, if not all, known molecules. That tutorial, which I'll link in the bottom, talked about how I set up the database originally, and then how I filled the database with records describing the molecular structure and the different names of each molecule as retrieved using PubChem. What I want to talk about today is once I have such a large database, which numbers somewhere in the order of 113 million molecules, how I can run queries against that. And I'm going to show you how to do that by going through the next step in this project, which was partitioning that database of millions of molecules into smaller subsets that are representative of different groupings of molecules. For instance, all those molecules which are known to belong to a certain class, or molecules which are chemically similar to those known molecules, or molecules that are at least capable of being in that particular class, in our case, energy or hydrogen storage molecules, but are selected at random. So given those types of queries, we're going to walk through how you do them efficiently using a database so you can get some ideas on how to work with a tool like MongoDB. So to quickly start off from where we left last time, let's start up the database. Just to remind you, what I've done is I've created a locally runnable version of my database. And by locally runnable, I can run it as a user on a supercomputing system rather than requiring, say, it to run as a service, which would require root access. So by writing this configuration file, I can launch my database by calling this. So here I've launched MongoDB in the background, and if you note from the organization file, I point to a database path, which is just a set of files and folders. So now I'm running the database on my computer without having to have root access, which is fantastic if you're a user of a shared resource. So we're not going to talk about how this database was populated, but just to remind you, what we have is a database that is running. MongoDB contains multiple databases. Each server contains multiple databases. Ours is called C-free. These are for carbon-free fuels. And that database itself contains a collection. The collection is named Molecule Records. And that, in this particular copy of the database, which is smaller than the full-sized one, the full-sized one I kept on a shared compute cluster. This is just a small version that I keep on my desktop. Has about 8 million molecules. And to go through and just show what this looks like, it's always good to pull out what a simple record or representative record is. And you can see if I run this find one query on the database and I give it an empty dictionary, which means there's no criteria. So in short, find the first thing in the database. You'll note that I've got for each molecule its chemical structure annotated a few different ways. And I've got all of the English and in some cases other language names for these molecules. Like this here is apparently acetyl carnitine, which I've never heard of before. But I can get out the chemical structure. I know it's the first molecule in PubChem, so I can probably go find some papers about it. This collection I set up to house all of these molecules, and this ID here is particularly important. This is a unique identifier for a molecule called an InChIKey, and because it's in this ID field of the MongoDB, that field is indexed. It must be unique, and it's stored in a way that's implicitly sorted. So you're going to see in a minute that queries run against this particular field, or key, rather, ID, are going to go very quick. And that's just to illustrate because there is a search index. So I'm going to call list indices, which is a MongoDB command, it's going to return this object, which contains a lot of stuff I don't fully understand, but you'll note that the key ID shows up in here, and this, I believe, means it's sorted in ascending. One means ascending. You can go onto MongoDB and find out a little bit more. Another quick aside before we get into the kind of meat of what I want to talk about today, you'll note here that the list indices command looks a little bit different in the MongoDB documentation than what you just saw me run. Here, note it's written with this, I think it's called camel case, where the first letter in many words are capitalized, which is a common style of programming you see in languages like JavaScript or Java, but is different than what one sees in Python. Python uses snake case, where I separate words using underscores, so it's sort of all flat. And the names of the equivalent functions in Python are named slightly differently. So that's something that's kind of neat to know about the documentation, and I believe they even warn you about it, that when you're seeing commands in the documentation, that they're going to be written slightly differently and might have a few different characteristics depending on which language you're using MongoDB from. So kind of cool. All right, so let's actually get into the meat of things. Let's talk about how to run queries. Now, the first query I want to show you is how to take all molecules that are from a certain list and add them to a data set. Now, one thing that, or a subset. So one thing that I skipped over earlier is I read in a database of SMILES strings that constitute all known molecules that my colleague Hassan found for a particular application storing hydrogen in the liquid state. There are 149 of these, and the first thing I did after reading in that database was to compute the InChIKey using RDKit. I read the molecule into RDKit, and then I write it out as an InChIKey. So this query here is going to find all of the molecules, let me get back to it, all of the molecules from that list. Then I'm going to add them to a set. Now, we'll show you a little bit more about what that means. So let's go back and run that find one command again, the one which I just deleted. Hold on a second. All right. The one thing down at the bottom, you'll note that each record holds a list of subsets that this molecule belongs to. So I want this query to take all of the molecules whose ID is in a list that I specify, and then adds to the set subsets the value known. So this command is not one that I knew coming in. The way that one learns how to write these complex commands is, of course, going to the documentation of MongoDB. Now here I'm running the update many operation, which is the way I update many records all at one time. And you'll note that its arguments take a filter which matches which documents you want to operate on, and then an update field which tells me for each of those matched documents which operation would I like to apply. And there's a language to MongoDB. If I go and click on this query selectors object, you'll see that there are a lot of different types of expressions I can use to match particular documents. And one of them, let's see, down here at the end, where is, yep, here we are. It was actually back up at the top. There's a command called n, which n takes a list of values. So when I'm writing one of these inquiries, I have the name of the field key that I'm trying to match. I have the word n, and then I have a list of values. So if we go back to my command, we could see match ID. For ID, find what is in a list of molecules that I provided. That's how I translate the query that I wanted to create to MongoDB language by going through the documentation. There's a similar process for the update section. So here, instead of looking at the query operators, I'm looking at the update operator expressions, which you can see one is add to set, Add to set gives me a particular operation where I list the name of the field on that record that I want to update, and then I list a particular value that I want to add to that list. So, yep, subsets is the key I want to add to, and I want to add the name known. So when I run this query, you'll note it's particularly fast. And because I've already run the database, it doesn't actually alter. I've already run this command before. It doesn't actually make any modifications, and I can see that from the result output. I can see that it found 85 records that matched the filter query, and it didn't actually update any of them because I had ran the command before. The value known was already in that subset list, so it didn't have to make any alterations. And this here is pretty cool. It did that search over 8 million molecules. It found the 85 and applied the operation in 13 milliseconds. And that's thanks to the fact that this key is indexed. If you'll note, if I run an operation here on trying to find all documents who contain the word known within the list subsets, that's going to take almost 100 times longer. Actually, more than 100 times longer. It takes 4 seconds. So that is the power of indexing. Subsets is not indexed, so the query does not run as fast. So that's something very important to know. That's before I designed this query, I ensured that the fields that I was going to be operating on, namely ID, were already indexed. How to set up an index is going to have to be a different YouTube video, but suffice it to say, here's a reason for why you want to listen to it. Now, the other thing that I did here is you'll note that I did update many, where I tried to match all documents before passing in, instead of operating on them one by one. That is particularly good because MongoDB has a lot of optimizations, like we talked about in our last video, for being able to operate on many documents at the same time. And let's say I try to update a single record that, that doesn't take much longer. It takes 1 millisecond. So yeah, indeed it is faster to be able to, or it is faster to operate only on one record. If you'll note, if you multiply 1 millisecond times 85, you get 85 milliseconds to be able to run the entire list of queries and do the update every document, which is slower than the 13 if I did them all at one time. So keep in mind when you're setting up these queries, think how few times do I need to invoke the database as you're designing them. Now, we'll go on to some more advanced examples to illustrate a few things, and I'm going to skip over part of this notebook. You'll see here I'm matching large numbers of documents, and I'm doing so instead of trying to match all, I think it's, 1 million molecules in a single query. I'm going to do multiple queries in this point because there is a limit of diminishing returns. If I provide a list of too many molecules to match, that's going to take too long for, or it's going to try to send too much data to the database at one time. 1 million molecules is a lot. So here I do split that into multiple chunks, but I'm still taking advantage of doing a lot of records at one time. So here I'm performing 5,000, or queries of 5,000 molecules to match against at one point. Well, let's go on to something more complicated. So here I'm going to show 2 different additional queries. I'm going to try to match all molecules whose smile string follows a particular pattern, that it contains this symbol, which means that there's a double or an aromatic bond. That's a sufficient condition for these molecules to be able to store hydrogen in them. And let's run this query. So this query is a little bit slow for a few different reasons. 1, this field is not indexed. 2, I'm applying a computation onto it. I'm running a regex command. So this is running a lot of compute on my MongoDB, and you can see that my #1 user of processing power on my computer right now, well, was MongoDB. Here I'm showing you the CPU usage via top. That's going to take about 30 seconds, only 14 seconds for it to happen this time because it's running that additional calculation. Now, the reason I did it this way was I did send that query and I had that computation get performed by MongoDB because it's going to be faster. Being able to run query, they gave me this particular function, so I can expect that executing a regex against a database string is going to be faster using MongoDB because everything is happening natively against the database rather than, say, running a query, sending the list of all smile strings to my Python process, having Python run the regex, and then using the result accordingly. If the database provides me an opportunity to run computations on my behalf, odds are it's going to be faster to do it that way. So that's another example of a slightly more complicated query. But let's get into some more kind of complex examples of queries that you can run. So here you'll note that I'm running a pipeline of multiple steps using this so-called aggregation function. So aggregation operations in MongoDB lets you run multiple steps of work against your database in one go. And let's describe what this one looks like. So here I'm going to run a match operation. So I'm going to find all documents which this query is true, that they are valid molecules for for hydrogen storage. Then I'm going to sample a subset of them, and then from that subset sample, I'm going to return only a single value. That is, I'm going to take that full record and I'm going to project it down to a list of smaller values. So this aggregation operation is great because I'm passing all of that compute work to happen locally in MongoDB rather than having to, say, run one query, send the results to Python, perform the next query, send the results back to Python, and then happen again. I'm passing it all for the database so the database can do it more effectively than I could in Python. And there are a lot of great kind of features of these aggregations. MongoDB, if I understand it correctly, though I don't know how, will optimize these queries for you. Additionally, no data is getting sent over the network between them. It's all happening locally, which is great if, say, my MongoDB is hosted somewhere besides on my own desktop computer. Cutting down network traffic is often a good thing. So there are a lot of kind of neat advantages. So the way that I set up this query is, of course, not because I knew exactly this programming language ahead of time. I went to their friendly documentation page, and I can see that it provides me a list of all of these operations which I can perform. Now, I don't remember exactly where the button is, but if we go over here and go to their reference, I can see in stages, they provide me all of these different verbs of things I can do, like, where is it? There should be, if I scroll down enough, sample, to create a sample. And I can dive into this page and see that its syntax is from sample, give it a size of documents that I want to run. That's how I gradually figured out what I wanted to do and then figured out how to translate it into the programming language with all of the different verbs and nouns which describe them. Sorry, I'm not going to go down the word figuring out whether I use noun or adjective correctly, but hopefully you got the idea. That's how I figured out how to set up this aggregation pipeline, which, because it's running on a database where it has the ability to operate on all of this data in memory without sending it to another process, is going to happen very quickly. So yeah, that is the tour here. One side thing I'll mention about this sample operation in particular, if you start running for very large databases, which 8 million is not large, that database is only 2 gigabytes, so I can fit it all in memory on my computer. This sample operation is not a problem because what ends up happening on larger databases is it has to store that data in a temporary location. If your sample is particularly large or it happens on a subset of the entire database, then MongoDB is going to have to do some extra work, which is going to take up a lot of additional memory or disk space, which becomes a problem. There are ways you can get around that if you want to create a sample operation, but that's going to have to be in another video because I've already spoken for about 20 minutes on this one. So yeah, just to wrap up, what we're explaining here is how to create queries on a MongoDB database, hopefully showing you the basic structure of these queries. A filter for an update operation tells me which documents. The update tells me what I want to do on them. And I found how to be able to operate on those by going on to MongoDB's documentation and seeing all of these different functions that it allows me to do. So that's your basics of MongoDB queries. I hope you're having a nice day, and I will talk to you in the next video.